Hi, I'm Sabir Liakat. I'm an engineer at Teledyne Princeton Instruments. Thank you for attending this seminar on LightField automation in Python for spectrometer and camera combination systems. A prerequisite, if you will, to this video is the first seminar I did on the introduction of the LightField automation interface via Python. It's highly recommended that you watch that video first, as it'll give you a good idea how to get acclimated into the development environment and how to automate LightField using Python. So here's what we'll cover in this seminar. We're going to walk through a Python script that'll automate LightField when using a camera and spectrometer combination. So we have a Pixis 400BX and an isoplane 160 system set up. We're going to iterate exposure times and grading positions and take in acquisition at each position. So in going through this example, we're going to come across events, and we're also going to come across synchronous and asynchronous functions. So we'll discuss how these work, and we'll talk about some benefits and some caution, or some things you need to watch out for when using these. And we're going to validate the automated experiment by checking the captured data and make sure everything comes out as expected. So let's go through a script that I wrote for this seminar. So I'm going to load up my Spider. Again, this is the development environment for Python that I like to use. As you saw in my first video, personal preference, I enjoy using Spider. You can use whatever development environment you want. So let's give Spider a minute to load up, and then we can go from there. Okay, so it's coming up. So my scripts are loading. So here, this is the script that I made for this seminar, the TPI PyDemo 1. So let's go to the beginning. So we start the declarations here. These are all the imports. As you can see, we import. Here are some of the function definitions. So we're going to skip these for now and start with sort of the main part, if you will. So here, just like in the first video, here's where the automation starts. We declare an automation object, and we open up a add-in instance of LightField. We create an experiment class. Here's the first new item for this seminar. Here's the auto reset event, and we'll get back to it in a moment and what that does. So we have the experiment object here. We're going to load the experiment. So here's what I call the experiment. Here's also something new. We're going to hook a listener to this experiment completed event that is in the experiment class, and we'll go over events really soon. So then we're going to set the value of the spectrometer settings member grading selected. So as you can guess from the name, and you can verify this going through that LightField help manual, which I explained in the first video. This will let you pick which grading on the spectrometer that you want. So this isoplane 160 that I have has 3 gradings. So we're going to choose the 500 nanometer blaze, 1200 grooves per millimeter grading, which is grading number 2 on turret 1. So these are all 0 index. So index 1 actually means number 2. And we're going to call this function initialize file parameters. So let's go to this function, see what it does. So these are just a bunch of set value commands in the experiment class. So we're going to set the file name generation increment. Um, this is whether we attach an increment or not, which is true. What increment number we start with. So date and time, we're not going to attach the date and time because these are false. So you can see that this function is just a way for me to get the file name generation the way I wanted, because part of this automation is not only are we going to automate the camera, I'm sorry, the spectrometer position and then have the camera take an acquisition, we're also going to name the file accordingly so that you can see exactly what went on. And a lot of researchers will want to do something similar to this, where they name their file in such a way where they can tell immediately exactly what was done in that experiment. So that's the initialized file params. And then I have a list of exposures. So 50 millisecond, 100 millisecond. and a list of spectrometer positions. So 560 nanometer, 435 nanometer, and 546 nanometer. And this is the base file name that I'm going to use. So all my files are going to be called, when the image is acquired, they're going to have the name tpi.pydemo.1 dot, and then you'll see in a bit, in the acquire function, we actually set the file name with respect to what the experiment parameter was for that acquired image. So here's the for loop. So it's a double loop. So we're going to look through the spectrometer positions. Then we're going to look through the exposures. So we're going to set a spectrometer position. So position 560 nanometers. We're going to take exposure at 50 millisecond, exposure at 100 millisecond. And we set value. So we set the grading center wavelength at the spectrometer position, which is in the outer loop, and the exposure time to the inner loop. And then we do this acquire and lock function. So when I do acquire and lock, I'm just going to print out acquiring, and then the name. So this name object, which you see I passed base file name here. I'm going to add on to this base file name this stuff. So the exposure time and then the center wavelength. So for each file is going to be named with the exposure time for that acquisition, and also the center wavelength position for that acquisition. And we get it right from the camera settings itself, so we know that it's accurate. See, we get the exposure time and then we get the spectrometer settings, we get the center wavelength. We get it right from the experiment object. Then we're going to set value, so the experiment settings, file name, generation base file name, and we're going to set it to this name because we tacked on to this base file name right here. And then we're going to finally give the acquire command, and here you can see this wait 1. So now let's get to it. So I mentioned the new item in this seminar. So where is this acquire completed? It's going to be right here. So this is an auto reset event, and it defaults to false. So what is this? It's a thread lock. And so what happens is when this acquire function is called, the acquire in the LightField automation is an asynchronous function. And an asynchronous function is something that does not lock a thread. So after you call this acquire, whatever lines get put next to it, they'll get run in the next clock cycle, or whenever whenever the thread runs its next command. So if I call this acquire function here, I can add some other things underneath it while the acquisition is going on. So for example, if I want to start an acquire and then I have some function generator or something that I can control through software, I can add that in. Or actually, as you'll see in my next seminar, we can use it to move a spectrometer asynchronously and get some real-time motion data out of it. So that's for the next seminar. But for this seminar, we're just going to call an acquire, and we're going to lock the thread right after calling the acquire. And the reason we do that is if I don't lock anything, so this is going to call the acquire, and then the next clock cycle, it's going to go right to the next position in this loop, and it's going to try to acquire again. So if you try to acquire before the other acquisition is finished, then LightField is going to crash. It's not a state that you want to put it in. So this way, this wait 1 command from the auto reset event class, it will lock the thread until this reset event is set, or is set to true. So you can find the documentation for this in Microsoft's .NET library. It's very simple to use, the auto reset events. There are also manual reset events and manual reset slim events, and they're all used for the same purpose, but they work in slightly different ways. So depending on the application or what environment you're using, you might want to use one or the other. But that's the idea. You want to lock the thread until until it's ready. And how does it know it's ready? So now we get into the idea of events. So we're going to backtrack to when I introduced this experiment completed event. So this is again a new concept for this seminar. Um, this experiment completed event is something that will give the software a trigger to to let it know that the acquisition is completed. So for the hardware-minded listeners out there, you want to think of this as a TTL logic signal to your device. For example, like let's say you're connecting a logic out of our Pixis, right? And you have it set to exposing. So it's gonna it's going to give a TTL high while the exposure is going on and then go back to low. And so feasibly, you could trigger a light source or something else with that rising edge when the exposed logic is going from low to high. So in that same vein, this is exactly like this is a software trigger. So this will basically so this listener hooking. So this is the syntax for what they call hooking a listener. So if the event is a trigger, you want something listening for that trigger. It's like on your oscilloscope when you set the trigger level to a voltage that you want, and then you arm it to acquire. Same idea. So you're arming the listener here, and then here's the function for that listener. So this is what they call the callback function, and basically, whenever this software senses that the acquisition is complete. So we're just going to print out a line saying the acquisition is complete, and we're going to set this event. So and you can cross-reference this with the material that Microsoft provides for the .NET reset event classes. Um, but what this set will do is actually put this auto reset event true, which means that the thread locking. I'm sorry, it'll make it back to false. So when you put this wait one there, that was like setting it to true. When this event is true, it means that you're going to lock the thread. You're not going to let anything else run on this thread. And then now I set this, and now I'm back to the false state where the thread can continue. So we're going to wait one. So we're gonna acquire. Then we're going to lock. That's what this wait one does. Once the acquisition finishes, because the listener is listening independent of the thread, so the listener is not locked. That's the beauty of using the event listener. Then you can set it, and now it'll be ready for the next iteration in the loop. So one thing I want to point out is you can use a couple of events, several events with the LightField automation. This is probably the most useful, experiment completed, and for the reason I mentioned, because the acquire is asynchronous, and you can use that to your advantage. We're going to open up this LightField add-ins and automation programming manual. Again, please review my first seminar on this. This covers a lot of very important material. You can find pretty much everything you need in this document. So we're going to control F events. Here, we're going to look through the experiment event. And as you can see, the other classes have events too, like File Manager has events, Experiment will have events. Let's go to the experiment events. You can see these are the events that the experiment class supports, and here's the experiment completed. So like I said, when the acquisition is completed, this event will be raised. So this means, if you're doing a take one look in LightField, it'll call back. If you're doing a live preview, every time a frame is updated, it will tell the listener to call back. If the acquisition occurs, if you're doing an acquire, every frame that gets updated, it's gonna call back. So um, when I do this callback function, if I were taking 20 frames in the experiment, and again, this is something you'll see in the next seminar, and it's very cool. Every frame will get updated live. So using this event is your way to get live data. So let's go back to this list here, and here are some of the other events you can use in the experiment object. And like I said, the experiment completed is probably the most useful and very cool event that you're probably going to want to use a lot once you sort of get the hang of it. Um, so yeah, so that's what this will do, it'll loop through and it'll collect at these exposure times and at these positions. So before we run this script, let's just open up regular instance of LightField. So we're going to open up LightField regularly without any automation. We're just going to kind of step through this experiment and just kind of give you an idea of what it should do. That way, once the automation happens, then you can kind of verify that the the correct actions happen, and then you could be confident that when you have a larger list of exposure settings or a larger list of spectrometer positions or both, or you're integrating other hardware, you can be confident that it's doing the right thing. So here we're loading the TPI PyDemo1 experiment, which is the exact experiment that we're going to load with this automation. But again, I'm sorry, this one right here. Again, we're not going to use the automation right now. We're going to just step through it and make sure that it works. So here, right now, the exposure setting is at 100. The spectrometer is at 546. So here's the idea. So, all right, let's just take a look. Hit F8 to take one look. So you can see I'm looking at some mercury spectra here because center wavelength 546. So this very strong 546 line is going to be right in the center. And here's a doublet, the 576, 579 doublet. Here, we're going to display as a graph. We're just going to look at the center row. So you can see here, 546 nanometer line, around 32K counts. So let's see what happens. We'll put it at 50 millisecond exposure. Take another look. As you can see, we have that line, and as you would expect, the exposure time, since now it's half, the signal roughly doubled. Now the light source we're using, it's an atomic emission source. It's not NIST traceable intensity wise, so it's not always outputting the same flux. So there's going to be a little variation. It won't be exactly half, but the idea is that you're going to reduce the exposure, you're going to reduce the intensity noticeably when you change this exposure back and forth. So let's move to another grading position. What did I have here? I had 435. So I move it to 435. So the spectrometer is moving. Exposure times at 100. So let's snap one. Now you can see the emission positions have changed because the grading moved. Now it's at a different angle. So now you can see the 436 nanometer line, and now here's the 409, or I'm sorry, the 404.9 or 405 nanometer lines right there. So we're going to step through the positions and the exposure times with the automation. Now that you have an idea of what I'm looking at, and here we'll display it as auto. So this is what it looks like with the full frame image. So let's get out of this. So we don't need to save the experiment because we're gonna use that during automation. So now I think we're ready to run the script. So let's go ahead and do it. I'm gonna hit F5. It's gonna run. So right now it's gonna open up an instance of LightField and add in process. So just give it a minute to open. It's opening, doing its thing. It's going to load, after it opens, it's going to load that TPI PyDemo1 experiment like we discussed. Okay, so let's we'll leave it in view mode because that's going to be the more interesting thing. So, and as soon as the experiment loads up, it's going to go ahead and fire away. So it's loading the experiment, as you can see. So once the devices get loaded, it's going to fire right up and go into that double loop. Okay, I hear the spectrometer moving, so, okay, see? Wow, so I already did the experiment, so it's gonna, I have the data files already saved, so I'm gonna do another run. I'm gonna resave all the data. You see it collected 2. It moved the spectrometer. It's gonna collect 2 more. It moved the spectrometer. It's gonna collect 2 more. Now the experiment is complete. So let's look at the data that was collected. So You can see here we recently acquired 6 images, and you could see the first image is saved as TPI Pi Demo 1. See, exposure 50 millisecond, center wavelength 560 nanometers. So the second one that was taken, it stayed at the 560 nanometer position. Now it went to 100 milliseconds. Now the third one that was taken, 435, 50 millisecond, stayed at 435, 100 millisecond. Then it moved back to 546, 50, and 100 milliseconds. So you could see that it did exactly the logic that we were expecting from that loop in the Python. So let's open up all of these images and just take a look at it to validate that everything was done correctly. So you can see these images look pretty good. Um, Here's the 6th one. So let's go to the first one. So you could tell from the file name that this is going to be 50 milliseconds and 560 nanometer position. So let's hit F7 to open up the file information, and let's look at the exposure time. You can see 50 milliseconds, and then the spectrometer position will be down here. See grading center wavelength 560. So let's go to another one. Let's just pick that guy, 546. So this is at 546. Open up the, again, let's just for exposure. So that's again 50 millisecond, just like as we said, and grading position 546 center wavelength. So you can see that the automation did everything correctly. So let's just walk through these really quickly. Again, we're going to look at the center rows just so we can have the wavelength calibration on the axis. So you can see 546 nanometer position, around 20K counts. And here's the 577, 579 doublet that I referred to earlier. And the center wavelength, you could see 560. So this will be the center pixel position. So we'll go to this guy right here, the 546 peak. Yep. So I picked the highest value. So you can see. Let's look through graph. So you can see there the exposure increased and the intensity counts went up as well. And now we're going to move to 435. You can see it already looks different, so that's what you'd expect. Here's the 436 nanometer peak, and then you can see it stayed at 435 center wavelength. Here's the 436 nanometer peak. Again, intensity increased with the increased exposure. Now we're going to go back to 546. So previously we had it at 560. So I'm sorry, let's look at this as a graph. But now so when I was looking at 560, the 546 position was sort of on the left-hand side a bit because the center was at 560. Now we're going to have the 546 peak smack in the middle, and we're gonna see that with the increased exposure time, the intensity increases as well. And you could see now the 546 is in the center, and you could still see the 577, the 579 doublet right there. So we've just validated that our script right here did everything that we wanted it to do. And you could already see that the file names are saved accordingly. So when you go to your LightField folder, so I'm going to do that really quickly. So here's my default LightField folder where I save the data. Let's go to the TPI demos. So you can see all of the images got saved. So TPI, so you were just looking through this file list. Oh, and these RAWs, because these files are background subtracting, these are just the images without the background subtraction, in case you want those. So if you do any corrections to the file, LightField will also save the uncorrected files, if you will. So here are all the files. You could tell. So I did some earlier experiments with the center wavelength 0. You could see that here too. So um, here's the center wavelength 435, exposure 50 milliseconds. So you could tell from these file names exactly what was done in this experiment. And that's a very useful thing you want to do in automation. And again, that's done through manipulation of these file name generation parameters, which are part of the experiment settings. And then when you actually do the acquisition, you can get the values right from the experiment object itself to be 100% sure that that's exactly what you're looking at. So that takes care of walking through this script. So now we can run this auto.dispose line. This is one way. This would be just like getting out of this automation add-in process here. You can click X, and if you want to do that through automation, you can just run this line, and you could now see the automation object is disposed. It went away. So that takes care of this script and the concepts in this seminar. Again, we went through the reset events. Where is it? Right here, and how that is useful for locking the thread. And why do you want to lock the thread? It's because we have asynchronous functions such as the acquire. The advantage of the asynchronous is you can run other lines that you want that get executed in the following clock cycles um, without having the thread locked up. So you can run this acquire and then program other hardware or arm something else via the software. And then when you've done everything you need, then you lock the thread so that you don't put the software or LightField specifically, you don't put it in any states that are bad. You don't want to corrupt it. And then we talked about and the opposite of asynchronous functions is synchronous functions. So synchronous functions lock the thread automatically, and you can see here that the when I set the center wavelength right here. So if I go from 560 to 435, the spectrometer is going to take some time to move. But you can see I didn't add any thread locking here because um, this is a synchronous command. So this will automatically lock the thread until it's ready. And you could verify that by we just validated those acquired images, and everything, all the results were exactly on the correct wavelength. So you, that kind of proves that the grading, the software waited enough time for the grading to move, and then it executed the next command. So that's a synchronous command. That's the opposite of asynchronous. The benefit of that is obvious. You can't mess it up. Like, you can't put it in a corrupt state because it'll lock the thread. It won't let you do anything else. It won't go to the next line. It won't go to the next. It won't execute the next command until this returns that it's free. So those are the asynchronous and then the synchronous commands. And then we went through the event. So the event is like a trigger. So like you have your hardware logic outs, it's now here's your software trigger. So you have a listener that's independently listening the whole time for this. Where did it go? Right here. This experiment completed to have happened. Once it does happen, so the experiment completed happens, quote unquote, once the frame data has been updated for another frame. And once that happens, you can run this callback function and you can unlock the thread again so that the next iteration in the loop can run. So, and you can see in this console output, I put the acquiring before I issue the acquire. I print that, and then once the callback returns, then this line prints out, and then I also unlock the thread. So thanks for attending this seminar and going through this video. I hope you found the content useful. You could see that even in something seemingly simple like iterating through different exposure times and spectrometer positions, some important concepts come up about thread locking and handling events. So if you have any questions or comments, feel free to send them to us at pi.techsupport@teledyne.com. Once again, my name is Sabir Leacat. I'm an engineer at Teledyne Princeton Instruments, and we thank you very much for watching.